Hello students, this is Dr. Ben. I'd like to work on a problem from Chapter 6 that has to do with work and kinetic energy. So we have a situation here where a car is our object of interest and it's traveling at a certain speed and it stops by putting on the brakes, and we're told that in the initial situation that the car stops in 50 feet. So from a certain original speed of 30 miles per hour, it takes 50 feet to come to rest. So we want to figure out for this same car on the same road, if it's initially traveling at 60 miles per hour, how long will it take it to stop? And so we want to solve this problem by using the work kinetic energy theorem. All right, so let's go ahead and do that. So we'll say that the work done by all the forces that act on the object is equal to the change in the kinetic energy. And we can see from the force diagram that there are three forces that act on the car. So we have the normal force, we have the weight, and we have the force that the brakes exert on the car. And two of those forces, the normal force and the weight, are perpendicular to the motion, which is horizontal, so they do no work. So it's only the braking force that does work. So the work done by all the forces is actually only equal to the work done by the braking force, and that's equal to the change in the kinetic energy of the car. All right, so we can use the definition of work to figure that out. So the work done by the braking force will be the value of the braking force, F sub B, and then multiply that by the distance traveled, and then times the cosine of the angle between the displacement and the force, and that's going to be 180 degrees in our case. The braking force is opposite to the motion, and then the change in kinetic energy is going to be equal to 0, the final kinetic energy, minus 1/2 mv original squared. All right, so I want to solve this relationship for the variable d, because that's the thing that we want to find in the new situation. So the cosine of 180 is minus 1, so I have minus the braking force times d is equal to minus 1/2 mv original squared. So therefore I would have the distance d, the minus signs cancel out, is mv0 squared divided by the braking force. Alright, so if we take that same relationship and apply it to the second case, then the distance traveled while the car slows down is going to be capital D, and so that'll equal the mass times the original velocity for the new situation divided by the braking force, which is going to remain the same. Alright, and so we can take the first equation and solve it for the braking force. So I get F sub B is equal to little m v naught squared divided by d, and then plug that relationship in. So capital D equals m big V original squared divided by the braking force, m v original squared times d. So that equals little d times v original squared for the new case divided by v original squared for the old case. And then plugging in the numbers for our particular problem, we would have 50 feet times 60 miles per hour squared divided by 30 miles per hour squared. So 30 over 60 is 2, and 2 squared is 4. So we have 50 times 4, which will equal 200 feet. So the stopping distance in the new situation is going to be 4 times as much as the stopping distance in the original case, because the kinetic energy goes as the square of the velocity.